Welcome to day 12, 3.7, optimization, part 2. So we're going to keep working with max and min problems, okay? So let's look at this first example. A person on a rowboat 2 miles from the nearest point on a straight shoreline wishes to reach a house 6 miles farther down the shore. If the person can row at a rate of 3 miles per hour and walk at a rate of 5 miles per hour, find the least amount of time required to reach the house. Okay, so let's get this picture first, okay? So a person is in a rowboat at that point P. They're 2 miles from the shore, so that's this right here. From that, on the shore, they're 6 miles from a house, okay? So that's this distance here. So we know that we can row at a rate of 3 miles per hour and walk at a rate of 5 miles per hour, okay? Our goal is to find the least amount of time. So that's key. Find the least amount of time. So that means I want an equation in terms of time. So we kind of have to remind ourselves, okay, distance equals rate times time, so that means time is equal to distance divided by rate. So we need to talk about time in terms of rowing and add that to our time when we're walking, okay? And we want to minimize this time, all right? Okay, so how do we talk about the time for rowing? Well, we should recognize that this is the hypotenuse of a right triangle here. So we can simply set up that the hypotenuse, that distance, is equal to the square root of the leg squared plus this leg squared. And the rate at which we're able to row is 3 miles per hour. So here's our distance rowing, here's our rate rowing. And now we need to add that to our distance and our our time walking. So our distance walking, well, whatever we went in terms of this guy, we have to subtract it from 6, okay? So 6 minus x is our distance that we're walking at a rate of 5 miles per hour, okay? So now we just clean it up, and I cleaned it up here so that finding the derivative is going to be nicer, okay? So remember, since we want to minimize the time, now here's where the calculus comes into play. Now we have to go ahead and find the derivative. Pause the video a second and see if you can find the derivative of t. Okay, hopefully you got what I got here, all cleaned up, okay? So we had to remember to bring that power out front, subtract 1, and don't forget the chain rule, and then taking the derivative of the next portion there. So then we needed to find our critical numbers. So we set this equal to 0. I kind of cleaned it up a little bit. If you have questions how I got here, let me know. And what we end up with is we end up with 2 critical numbers. However, I throw this negative 3/2 away because we're not going to have any negative distances. So that's outside of our domain. Now we're ready to set up the first derivative test. Okay? And what we should notice is that from 0 to 3/2, our first derivative is negative, and then 3/2 to 6, we're positive. So t is going to be decreasing and then increasing, so that means we have ourselves a relative minimum at 3/2. All right, so by the first derivative test, we have a relative minimum when x equals 3/2 miles, so the least amount of time required to get home is going to be when we plug 3/2 into our t function, and we get about 1.733 hours. Okay, this next one I want you to kind of try on your own and then check your answers afterwards. So the first thing we need to do is find the maximum volume. All right, so if I'm asked to find the maximum volume, I know I'm going to need an equation in terms of volume of a right circular cylinder that can be inscribed in a cone of altitude 12 centimeters and a base radius of 4 centimeters if the axes of the cylinder and cone coincide. So first let me show you the diagram, and then I want you to see if you can take it from there. So pause the video a second, let's get the diagram ready to go. Okay, so we have this right circular cylinder inside of a cone. Okay, so that's this guy right here. So now what we want to do is we want to zoom in. We were told the altitude of the cone is 12, all right? And the base radius is 4 centimeters, all right? If the axis of the cylinder and the cone coincide. So it's going to look something like this, all right? So that's 12. This whole radius is 4. I'm going to call the height of our cylinder h, and I'm going to call this piece, this would be 4 minus r, if r represents the radius of our cone, or sorry, of our cylinder. So now what you should remember is that if we're talking about the volume of a cylinder, we have volume equals pi r squared h. Well, this is two variables, r and h. So what we want to do is we want to use this setup over here, all right, to get h in terms of r. So how are we going to do that? Hopefully you recognize we can set up similar triangles. So we can set up the proportion 12, the height of our cone can compare to the height of our cylinder, 4, the radius, this entire radius here can compare to this portion of this small right triangle, 4 minus r. So then we would get h is equal to 12 minus 3r. Okay, so now you have h in terms of r. Come up with your volume equation. Then you need to find v prime, okay, in terms of r. Go through your first derivative test, and we're looking for a maximum. So give it a try and check back when you're done. Okay, so hopefully you were able to say, okay, volume equals pi r squared h, so we substituted 12 minus 3r for h, and we got our volume equation here. Now we needed to take the derivative, all right, and I factored it right away. Setting it equal to 0 gives us two critical numbers. So setting up our first derivative test, I'm going to get v prime is negative to the left of 0. It's positive between 0 and 8/3, and it's negative after 8/3. So then our volume is decreasing, then increasing, then decreasing. So it tells us we have a relative maximum by the first derivative test, okay, at r equals 8/3. So now we can maximize the volume by plugging our radius of 8/3 into our equation that we got prior to this, and we get our maximum volume of about 89.4 centimeters cubed. If you have questions, make sure you ask in class next time we see each other.